Our third example of net forces is the most complicated. It's net forces involving ropes or cables. And what makes that special is that when we look at all the masses that are connected by a rope, in this case I've got a table, I've got a rope and a pulley here, those two masses are connected by the rope. We got to remember that that whole thing is going to move all together. So not one of these masses isn't going to accelerate quicker than another. They're all going to move together, and so it forms this system that's linked together by a rope. So the question here is that we got this 5 kilogram mass sitting on a table, an 8 kilogram mass hanging over the edge of the table, connected with a rope and a pulley. Clearly someone is holding this to start with, otherwise it would be already moving. So let's assume somebody's holding it and they just let go. The question is, determine the acceleration of the system if there is no friction. So if there's no friction between the 5 kilogram mass and the table, then when we look at the net force diagram on this, or free body diagram on this system, the mass that's on the table has a gravitational force that's down. We'll call it mass 1. And it also has a normal force up. And those two forces are balanced out. On the other hand, and there's no force friction. So in the first part of this question, there would be no force friction. That's why that's in red, because there isn't any in the first part of the question. And so I don't know how I got my pulley way over here not connected to the table, but you'll have to put up with it. And the rope goes to the pulley. This mass, on the other hand, is going to face a gravitational force down as well, but there's no normal force holding it up like this one. And so when we consider all the forces that are acting on this system, the only force that we really have is this one. These two forces are balanced in an opposite direction, so they cancel each other off. And so our net force is just going to be the gravitational force of mass 2. So that's just going to be mass 2 times the gravitational acceleration. Well, the net force, what's unique about it is, because we said the whole system is tied together with this rope, then in terms of the acceleration, it's the total mass, or the 5 and the 8 kilogram mass, that is going to be pulled by this one force. And so here, when we go MA, we're talking about the total mass. But here, when we're looking at the gravitational force, the only gravitational force that's unbalanced is the one that's acting on the 8 kilogram mass. So that's why it's only 8. So if you take 8 times 9.81 and divide by 13, you would get a 6 meters per second squared acceleration of that system. Well, part B throws some friction in the question. What happens if there's a coefficient of friction between this mass and the table? Well, the only thing that changes in this whole system is now we've got a force friction here in red that's going to oppose this whole system getting pulled by this mass. And so when we consider the net force, it's still going to be the gravitational force of this mass, but now we're going to subtract this force friction that mass 1 is experiencing. And so when we set up our equation, force net is force gravity on mass 2 minus the force friction of mass 1. The force gravity on mass 2 is just mass 2 times 9.81. The force friction on mass 1 is going to be mu times mass 1 times g. I give you the coefficient of friction here, so then you can make use of that. You got the mass. We're going to subtract those two forces this time before we divide by our total mass of 13. In this case, the whole system ends up accelerating at a smaller rate because the force friction kind of holds everything back. You know, this type of situation, if you're thinking about a real type situation of that, maybe you are standing on top of a cliff holding onto a rope and pulling your friend up the cliff. Well, if you don't have enough force friction between your feet and the ground, you're just going to get pulled right off of that edge of that cliff as well. And so it's really important that we realize that with ropes, all the masses are going to move together. They can't possibly have this mass move in that direction and that one move in that direction because they're tied together. And that's what makes net forces involving ropes a little more complicated.